And okay, so before we start, today we're going to try to recreate a true face-to-face interaction as much as possible. I know that we're online and some people are sick of that, and that's, you know, that's good because that's your social part trying to being expressed. And I should say that your learning is my priority for today. So I'll have you do several things right now. And the things that I'll have you do are strategies for better focus. Okay? So we're gonna try that today. If you would like, try them today. And you're welcome to keep using them on your online meetings as well. So if you're able to, I'll have you turn on your cameras. So for the people that were here early, I told you that I would ask you to do that. So in the meantime, I want you to turn on the cameras, because it turns out that educators can better tailor their teaching if they can see you. Okay? Learning is, after all, a social enterprise. Okay? If you're able, number two, if you want, this one is this one's gonna sound weird, but hang on. Go to your self view in Zoom and turn it off. I don't know if you tried that before. So it turns out that checking yourself out in the camera is really distracting. So no scientific literature needed for that one. And it's liberating too, when you're not able to see yourself, because in a true social interaction, you wouldn't be able to see yourself. You'll see. Okay. Now, third, this is my third strategy for better focus. Silence and hide your phone where you cannot see it. Yes, the research says that just having your phone visible is detrimental to your attention. The reason is that deep thinking releases stress hormones. So that leads your brain to want to check your phone for entertainment or dopamine. Okay. But if you cannot see your phone, that effect starts going away. Okay. For the people just coming in, I was asking everybody to turn on your camera and hide your phone. Yes, really. Okay. So several weeks ago, Dr. Ross invited me to speak for a RISE seminar. And I've given RISE talks before, but never a full seminar. So today is my first RISE seminar. So I was like, qué cool. And I've heard that usually people come here to speak about natural sciences. I'm a biologist, but I was like, Ross, this is very cool and all, but can I change the whole purpose of the seminar? And he was like, what do you mean? And I said, I think, and I feel like I should talk about science education instead. And Ross said, science education it is. So I'm Daniel de Jesus. I got my bachelor's diploma in biology from the University of Puerto Rico at Cayey. Currently, I am finishing a degree in ecology and evolutionary biology at Texas A&M University. And just 2 weeks ago, I got accepted to start a PhD in science education at Texas A&M University. Yeah. And I'm an educator, so I'm going to really make you think. And for that, I want to listen to you too. So this is my first question for you. In what ways do you think science classes have not promoted your long-term learning of science? In what ways do you think the classes that you've had during school, during university time, have not really promoted your long-term learning of science? And I knew that this question might have been a little complex. So I have an example for you, so you have a better sense of what I mean. Okay? For example, I've never understood for science laboratories Why, oh why, did we have to copy the lab instructions word by word to our lab notebook if we already had it on the lab manual? To me, that was a waste of time. I'm sorry, Robert Ross, but and a common part of science classes that promote mindless, shallow thought copying instead of actually helping students learn the lab content. So this, for example, never helped my long-term learning of science. So in what other ways do you think science classes have not promoted your long-term learning of science?
Sometimes when teachers or professors teach like directly from the textbook, it's basically makes the class a little less interactive, and like it makes the process of learning for students difficult because they can't like properly visualize why it is important and how they can like apply what they're learning to real life. So I think that affects it.
Yeah.
Sorry.
Go ahead.
I've had teachers in the past and professors just read straight up the sentences from the PowerPoint. And I feel like that's just kind of a waste of time because I can read. So why would I go to a class when I can just read what's there? So I really like when the professor like makes us think and gives us examples and different things, like not just read from the PowerPoint because anyone can do that.
Yeah. In what other ways do you think science classes have not promoted your long-term learning of science?
I was never a fan of my biology class in high school. Sorry, I know you do bio, but it was mostly a memorization class. For the most part, if you could memorize the bolded words in the textbook or the repeated points that the teacher would make by the PowerPoints, of course, then you could get A's. That's how you pass the class, by memorizing. So I wasn't a fan of needing to memorize science. That didn't seem right.
And see, we've mentioned several apparent problems in science education. And this is a thing. This is not limited to just specific things like the ones that we shared. In general, this happens too. Many scientific studies point to the fact that school science and even university science courses are not promoting much conceptual understanding. Okay? And by conceptual understanding, I mean a genuine, accurate, nuanced, and long-term learning of scientific ideas. So conceptual understanding is not memorization. It's not memorization for passing tests and getting good grades. Getting good grades, by the way, is not the same as accurately understanding complex science topics. Furthermore, currently, more than 70% of adults and 90% of high school graduates in the US are scientifically illiterate. And in Puerto Rico, the situation is the same or probably even worse. And this affects university graduates as well. And that may come off as a little surprising that university graduates are also in this category, but I'm going to show you what I mean. I'm going to show you what I mean. And for that, I'm going to stop this share real quick. And I'm going to go and show you a video of what I mean. So I'm going to share my screen again. And I'm going to go to here. And I trust that you can see what's on my screen. If you do see what's on my screen, I'll have an audible yes from you.
Yes.
Yes.
Thank you.
Yes.
So let's go ahead.
Karen Lee Fingerman, candidate in arts.
Despite a lifetime of the very best education, students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happens because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
I took physics, planetary motion, and relativity, and electromagnetism and waves.
I've never really had a scientific background whatsoever, and I got through school without having it. I've gotten very far without having it.
I had quite a bit of science in high school, yeah, through physics, first year, and 2 years of chemistry.
Regardless of their science education, 21 of the 23 randomly selected students, faculty, and alumni of Harvard University revealed misconceptions when asked to explain either the seasons or the phases of the moon.
When it's further away from the sun, then it gets colder.
The Earth's position interferes with the reflection of the sun against the moon.
Class 1924. The class of 1925.
To test how standard instruction succeeds or fails in reversing such misconceptions, we interviewed 9th grade students from a nearby high school. The students selected had little training in astronomy.
When it's winter, it's when the sun is farthest away from the earth, and when it's summer, it's when the sun's closer to the earth.
Why is it hotter, say, in the summer than the winter?
It's hotter in the summer because we're closer to the sun than we are in the winter.
Here's the second part.
Here's a seed.
Okay.
Okay, now hold on to that for a second.
Okay.
Imagine that I planted that in the ground.
Okay.
And a tree grew. All right, and here is a piece of that tree.
Sure.
Okay. Now, where did all that stuff come from?
So where do plants come from? You look at these beautiful big redwood trees, these great spreading valley oaks, and you know they start from this little tiny seed. It's miraculous. Where does all that weight come from?
The mass came from a lot of things, I'd guess. I'd guess from water that it sucked up from the ground. I would guess from minerals that it sucked up from the ground.
Water, light, soil.
Well, I suppose in terms of raw mass, most of it's probably derived from actually matter in the soil itself.
And some of it comes from water, obviously, but a large amount of it comes from the nutrients that the roots absorb from the soil.
Now, what would you say to someone who said to you that most of the weight of the tree came from the carbon dioxide in the air?
I would say I would have no idea. I'd have to think about that.
I would disagree because this same volume of air wouldn't weigh this much unless it was highly compressed.
I said that's very disturbing and wonder how that could happen.
It's a very strange idea that somehow the air, which they view as nothing, as weightless, as insubstantial, somehow makes a tree, a giant tree that weighs several tons. I mean, that's absolutely incredible.
That'd be hard to believe because carbon dioxide is, well, it's a gas, and it doesn't seem intuitive that you could add mass taking in a gas.
But that's where it comes from. It takes those carbon molecules and packs them together via chemical reactions so tight that you get this huge mass. So what does it mean that these Harvard graduates don't understand the fundamental idea of photosynthesis? Well, it's symbolic of the state of the nation. These are the best that we produce. They don't understand it. After all these years of school, who does?
You guys, and this was in university science graduates from Harvard and MIT. They showed the same scientific misconceptions, the same incorrect science ideas as middle school students. Okay. I'm gonna share my screen again. And so university graduates often show the same scientific misconceptions as school students. And you might say, okay, but this documentary was old. But no, the research says that this is still happening, and it's not limited to physics. It's happening in chemistry, biology, astronomy, and pretty much all scientific topics. And what's worse is that this doesn't only affect young science students, this also affects adults and the rest of the public as well. And this is evidenced by the poor social and science decision-making by policymakers, a little combustible material here, but the public opinion on scientific issues as well. Okay. So it's like, what the H is going on? Right? That leads us to the current state of science education. And in the current state of science education, we know that number one, conceptually understanding science is crucial. And we know this because of all the problems that we've seen so far when people do not conceptually understand science. And here's the thing. Much scientific literature is well established already regarding the importance of promoting conceptual understanding, but it is rarely implemented. And you see that when scientists ask teachers and educators about this, one main excuse that they give is, what do you think it is? Time. Okay. And for example, if you take a complex scientific idea that could take 2 years to really comprehend, and you condense it into 2 weeks of class, it's way too much material in way too little time. But you still would want your students to do well, so you test them on trivial things. So we often overwhelmingly see meaningless emphasis on vocabulary and recall of information rather than emphasis on the fundamental science ideas necessary for STEM careers and informed decision-making. Because like, what good does it do if students memorize a periodic table if they don't really understand the trends of properties among the atoms? Or what good does it do if they memorize the formula for photosynthesis if they don't really understand how it works or the biological significance of the sun's energy being turned into digestible food for the plants? And so what's happening, it's the so-called a mile wide, an inch deep philosophy. We're covering vast amounts of material that students will probably never learn in a deep way. It's like this quote by George Nelson that says, "You wouldn't be asked to name all the parts of a car when you're really trying to understand how transportation works." Okay. So ironically, educators feel the pressure of time from policymakers and absurd curriculum decisions. But if we don't teach for conceptual understanding, we are largely wasting our time and money. Science faculty time and student time is too precious and too important to waste merely on covering content that is not truly understood. So what should we do? Well, first of all, we have to pay attention to the scientific literature on education and learn about how people learn science. And you see that we already have our number 3. And in the current state of science education, we know that number 3, we should apply what the scientific research says, not our experience, to our teaching. And why? Why is it the case? So this is a question for each of you, okay? My question is, what are some reasons why you think we should apply the scientific research, not just our experience, to our teaching?
I would guess because sometimes our experiences are not the best. So if you have a bad experience taking a class or teaching a class, you wouldn't want to repeat that. So you would go search up what are some better techniques to learn and to teach.
Yeah. What are other reasons?
Maybe because
I think,
sorry.
Well, I think, for example, I am a chemist, so I have a lot of experience in chemistry, but if I am supposed to give a class in biology, I have not a lot of experience there, so I can't only rely on my experience.
Yeah, what I was going to mention is basically in that line, everyone has different experiences. I see that someone commented that in the chat, and maybe scientific research takes into account a sample of people, a sample of different people. And maybe that's why we should refer to scientific research.
I have Bianca Quiñones writing in the chat that everyone could have a different experience. So it's a way of being not standardized, is what I think Quiñones Bianca means. So there's another. Alexander Ortiz Rivera commented on the chat, objectivity. Alexander, what do you mean by objectivity?
What I mean is that if you use your personal experiences, it's not giving an accurate representation of the topic that the professor wants to teach. They're giving their experiences, and what they think of the actual topic, but not the basis of it. Mm.
What are other reasons why you think we should apply the scientific research, not just our experience?
I also didn't know how people learn science until I went to the research and read from the literature what we understand about how people learn the science. It made sense to me that if I want to teach science, then I should probably teach it in a way that people will actually learn it. So then my next question would be, well, then how do people actually learn this stuff? And there's, lo and behold, there's some research on that that says, oh, these are the ways we know that people learn.
And that's a thing, you guys. The literature indicates that educators tend to teach according to their experience or what's familiar to them. However, this often leads to behaviors and strategies, often leads to teacher behaviors and instruction strategies that have been shown by the research to be ineffective, unfortunately. So it seems like the best would be to rid ourselves of our preconceptions of how we should teach and start basing our instruction on what the research says to be effective. So let's try to step back for a moment and try to summarize what we've seen so far. Yeah? So in the current state of science education, we know that conceptually understanding science is crucial. And by conceptually understanding, I mean a genuine, deep, long-term learning of science. Number two, even though we feel the pressure of time to move quickly through the topics in order to cover more, ironically, if we do not teach for conceptual understanding, we are largely wasting our time and money. And number three, we should apply what the scientific research says, not our experience, to our teaching. And all research makes clear that the focus must be on fewer concepts that are truly fundamental to the purpose of the course in question. So now I'll do my part and emphasize that I won't have enough time today to teach how to teach for conceptual understanding. Talking with you for 40 minutes is not enough time for me to promote in you a deep understanding of the intricate issues that we've mentioned here and their potential solutions. But I'll try to do one more thing before we go. And what I'll do is that I'll first give you quick recommendations about how to improve your teaching. And second, I'll try to point you towards some resources that will assist you in moving forward, in implementing practices that promote conceptual understanding. So my first quick recommendation is to build a welcoming environment in classroom for students. Say hi to each student. Make each of them feel seen. Teacher behaviors are super important to set the right environment. I've tried to exhibit some of the right teachers' behaviors here, and we need to make students feel comfortable in our classrooms because that is the only way in which we'll be able to have them open up and share what they really think. And only when they share what they think, that is your opportunity to show them how their ideas are flawed. In other words, your opportunity to teach. But to do so, or to do that, do so through open-ended skeptical questions that make students think deeply about the science topics instead of using memorization. So use something similar to what's called the Socratic method. Now, this is a quick question for you. What type of questioning is involved in the Socratic method?
You have to analyze and think critically in the Socratic method, at least from my experiences in it.
You know, the story of Socrates is really interesting, how that person, even from antiquity, had a system of questioning that nowadays is still somewhat relevant to the education, to the world of education. And Socrates, what he did is that he asked questions. He didn't necessarily tell people information. He asked people questions in order to try and show them through their own answers how their ideas are flawed. Okay? So use something similar to that, because we want people to figure out by themselves how their ideas are not working as well as other ideas. So we really need educators that engage students in wrestling, fighting the hard battle with information. You can do this via interactive presentation of information and application assessment. You need them to be able to apply what they're learning. Okay. Quick recommendation number 3, be extremely respectful and emphasize that A, you care for them. Some students may not have heard those words in a very long time. And you guys, my education saved my life. I'm being honest. Just one high quality course is what's needed to save a student's life for the better. But the opposite is true as well. If we are careless with our teaching, we may turn away any number of students from science forever. So for that, emphasize as well, B, that their learning, not the course, is your priority. Let them know. So for some of the resources that I want to share with you today, look for teaching and learning programs or courses in your university. Look for places to familiarize yourself with the research in science education. Also, check the theories on how people learn. Pay special attention to the well-supported theories on how people learn, because much of the research that we have is based on these 4 well-supported theories about how people learn. So being at least acquainted with these theories will definitely guide you to discern good from bad pedagogical decisions. Okay. And also beware of the fads. So always run teaching models through the scientific literature lens. And what I mean by that is that fads are teaching models that are not wholly based in the scientific literature. Usually they're literally just models people have developed through their experience, but when they're tested, they don't hold up. They're not effective at improving student learning. And it might surprise you, but I would bet that most of you, if not all, have had an experience with at least one education fad in your lifetime. I'll give you a couple examples. Some examples of fads are the flipped classroom. You may have heard that one before. Learning styles, unfortunately. And learning styles is the one where we say, I learn better through hearing, or I learn better through doing, or I learn better through seeing. Okay? So keep your eyes open for that. Okay? Now, lastly, and of course I am biased, but listen to this. Texas A&M has a fantastic science education program. And you can make a career in these topics. And in terms of people, I suggest each of you talk to either Professor Michael Clough or Professor Joanne Olson. I have the highest of admiration for these people in many ways, including in the sense that they are excellent science educators and they have decades of experience training other science educators. So they are absolutely worthwhile talking to about how to improve your science teaching. They are always happy to help and improve people's education in any way that they can. So please let me know if you're interested in contacting these magical people. Okay. Now, you guys, this is the title for my seminar. Now, this is a question for you. Why do you think I named my presentation like this?
I think it's because if you don't understand the scientific knowledge that's out there, it doesn't matter if it's there or not. If you don't understand it, it's as if it doesn't even exist.
What are other reasons why I might have named my presentation like this? Producing scientific knowledge is not enough. How to become an effective preceptor of science. What do you guys think? And I do intend to wait and know what you guys are thinking. And I welcome anyone. I'm sorry for, go ahead.
I was just going to say, I had to look up the word preceptor. It means a teacher or instructor. I think you're trying to really point out that difference between knowing the science, knowing the ideas, knowing the concepts, as well as being able to communicate them.
So, yeah, so one of my intentions with this seminar was to argue that we scientists sometimes obfuscate in the process of doing science and often forget that we are proponents and educators, preceptors of that knowledge as well. We need scientists that not only can produce scientific knowledge, but can accurately share it as well. Like the quote says, being a science teacher is easy. Being an effective science teacher, on the other hand, is hard. But I am sure that with the right tools, I know that you'll be very well on your way towards being an effective preceptor of science. Thank you.